Anything else? Other questions? Is there anything else? Okay, then, so in that case, let's continue with the last section, basically, of this chapter. And we will look at graphs of tangent, cotangent, secant, cosecant. Okay. Now, if you remember from the unit circle, for any angle that is a central angle in standard position, we have this piece, which is sine alpha, and we have this piece, which is cosine alpha. These functions are what I like to call, if you remember, friendly. By friendly, if you remember, no restrictions. No headache. No problem. I never have to worry about the domain. It's in the category with other functions for which I don't ever write restrictions. Polynomial, exponential, absolute value, right? We don't ever write restrictions. There are no restrictions. Well, these are not friendly. These functions join the category of not friendly functions. I have to worry about the domain, worry about the domain, worry about the domain, worry about the domain. Why? So let's start with tangent. Tangent x equals sine x over cosine x. When is tangent undefined? When what?
When cosine is 0.
Absolutely. Absolutely. So that is a problem with tangent. Every time cosine is 0, tangent will have what? How is this called? When tangent is undefined, it has what? Okay, when a rational function was undefined, what did it have?
A whole or a vertical asymptote.
I knew I would get caught on that. Yes, of course. Absolutely perfect. Perfect answer. I could have not answered better, of course. So tangent x has vertical asymptotes. That's a problem. Okay. So remember also that the period for tangent is pi.
Can you show that last page on top?
Of course, yes, of course. Okay, so we know that now the tangent has vertical asymptotes, like the other three as well, of course. But where are they? So let's see, because we have to draw the asymptotes first. So pi over 2, pi, 3 pi over 2, 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Okay, so now back to the unit circle. We already know the coordinates of these points. Can anyone quickly tell us when is cosine 0? Just for a complete rotation. Because you can say indefinitely. Infinite. Yes, I agree. infinitely many times, infinitely many times, infinitely many times, but just on 0 to 2 pi, can anyone tell us when is cosine 0? Based on the coordinates of these points, we know immediately when cosine is 0.
You want like the degrees, like 180 degrees?
Cosine is not 0 at 180 degrees. Cosine is measured on the x-axis.
Okay.
But yes, that's what I want. But it's not at 180 degrees.
Is it 270?
Yes, this is one of them. 3 pi over 2, correct? Very good, awesome. So at this point, cosine is 0. And
Pi over 2?
exactly, awesome. Indeed, so also here, cosine is 0, because it's measured on the x-axis. Here is -1, here is 1. Only at these points, cosine is 0. Excellent, perfect. So I know where tangent will have a vertical asymptote. Every time cosine is 0, that's where tangent has a vertical asymptote. Okay. As you just told me, pi over 2 or 3 pi over 2. Negative pi over 2, negative 3 pi over 2. And it goes on forever in both directions, of course. Okay, we're ready to graph it. So remember, this is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. This way, 0 to negative pi over 2. This will be the fourth, because it's 0 to negative pi over 2. Fourth, and then the third, and then the second, and then the first. Good. So in the fourth, I'm here. So sine is a tangent. Back here, I just wanted also to say this. So these are the vertical asymptotes. At these points, where sine is 0, tangent is 0. So at 0 degrees or 0 radians, and here at pi or 180 degrees, tangent is 0. 0, 0, 0, 0, 0. And now I have to follow the quadrants. Okay? So negative in the fourth quadrant, positive in the first. Negative in the second quadrant, positive in the third. Negative in the next, positive, negative, positive, negative, positive. And as I said, it goes on forever. This is function tangent x. Okay, let's look at cotangent, which is cosine x divided by sine x. Where is this undefined? When
Sine is 0?
oh, of course, thank you very much. Brilliant. Exactly. Okay, so let's look at the unit circle. Where is sine 0? Because I know the vertical asymptotes will happen when sine is 0. Where is sine 0? Remember, we know the coordinates, and we know that sine is measured on the y-axis. Where is sine 0?
0 and pi.
Excellent. Great job. Exactly here. Sine x is 0 here. Sine x is 0 here. Excellent. Good. And where is cosine 0? You already told me. We already know. Cosine x equals 0. Cosine x equals 0. So let's graph cotangent. So my page 3. Da, 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 da. So 2 pi, negative 2 pi, negative 3 pi over 2, negative pi over 2, pi over 2, pi, and 3 pi over 2. Okay, first the asymptotes, where sine is 0, but sine is 0 is here, and here, and here, and here, and here. And of course, it goes on forever in both directions. So here's the graph. Between 0 and pi over 2, this is the first quadrant. Everything is positive. In the second quadrant, cotangent is negative. Positive, negative, and so on and so forth. Positive, negative, positive, negative. When you graph it, you should always start with the first and second quadrants and then just follow the pattern. So this is the graph of cotangent x. It has problems. It has problems where sine is 0. Tangent again has problems where cosine is 0. Okay. Let's take a look at secant and cosecant. Secant, by definition, is 1 over cosine. And yes, I know you're going to say, when cosine is 0, we already graphed when cosine was 0. And I will just copy the same vertical asymptotes. Negative 2 pi, negative 3 pi over 2, negative pi over 2, pi over 2, pi, 3 pi over 2, and 2 pi. Vertical asymptotes, where cosine is 0. Here they are. Okay, so all these, of course, are vertical asymptotes. Sorry, I should have put arrows here because they are vertical lines. Okay, perfect. Now, cosine in pencil. In pencil, I'm going to graph cosine. And you'll understand in a minute why I'm graphing it in pencil. So now I'm ready to graph secant. So at this point, and at this point, and at this point where cosine is 1, negative 1, 1, negative 1, boo-boo. Where's my eraser? Boo-boo here. My pencil. Okay. So notice what I just did. I graphed this graph of cosine. I will erase it. It was just to help me graph secant. First and fourth. When cosine is 1, 1 over 1 is this point, and it's the minimum of secant in these two quadrants. Here's the maximum of secant in these two quadrants, and this is a point of the secant. And now I go on forever. And this is the graph of secant x. Not this. this, 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 this. Cosine only helped me keep the graph in shape so that I can identify these points correctly. The minimum, the maximum, the minimum, the maximum, the minimum. That's all I needed the cosine in there for. Okay, final graph. That is the graph of cosecant. And we know the cosecant x equals 1 over sine x. So sine x, we know, is 0. Negative 2 pi, negative 3 pi over 2, negative pi over 2, pi over 2, pi, 3 pi over 2, 2 pi. So sine is 0 at 0. At pi, at 2 pi. Of course, these should have arrows because they're asymptotes. Okay? Now, of course, in pencil, I'm going to erase it. I'm going to graph my sine just to help me keep the graph in shape. Okay. Now I'm ready to graph cosecant. Okay. Now I don't need sine anymore. It just helped me because it's 1 over. Okay. This is basically it about these functions. Let's just look at a couple of examples and let's move on. I'm not going to ask you to graph these by hand, but I would like you to remember the shape. Please remember these shapes. Look at them and just graph them by hand just for yourselves a little bit. So again, period. 2 pi for all of them. All 4. A pi, sorry, only for tangent and cotangent. So please remember that. So let's look at just one example, 30. So y equals 1/2 cosecant 2x. So they want us to determine the period and have an idea of a graph. And we're going to graph it together. Okay, so first of all, the period of this function is pi over the number in front of x. So as you see here, for example, cosecant, because I have this example and I have the graph. Notice that the period of cosecant is 2 pi, as expected. Everything is 2 pi except tangent and cotangent. So this is 2 pi. But because of the 2, for this function, the period will be in the viewing window from 0 to pi over 2. So I will see this piece and the asymptotes, both the entire graph between 0 and pi over 2. So half of it will be right here at pi over 4. So I will have to see a graph, this piece up here and this piece down here. Okay, now the 1/2 in front shrinks the graph. It's not a vertical stretch, but a vertical shrinking of the graph. Okay, so let's see. I'm going to share my screen. That's wrong mouse, sorry. Okay, that was for the other computer. Where am I? I'm here. Okay, so there is, in the graphing calculator, we do not have cosecant, but cosecant is one of a sine. So I will put the 0.5 in front, and instead of cosecant, I put parentheses, I put 1, I put divide. There are different ways of writing this. Sine 2x, close and close. And this is 0.5 cosecant of twice x. I know that now I'm going to the viewing window. Allow me to